Hi everybody, my name's James. I'm joined today by Tristan, and together we're going to be exploring the question, is fusion power viable? We're going to begin by giving a brief overview of what fusion is and how we go about making it happen. Then we're going to discuss three of the major technical challenges that fusion needs to overcome before it can become a viable power source. And then Tristan will talk you through some of the social and economic issues surrounding fusion and fusion's place on the global energy landscape. So I'll begin by talking about what fusion is. So fusion is essentially a nuclear process where two light atoms like hydrogen collide at extremely high energies and their nuclei fuse together. And when this occurs, vast amounts of energy are released. On the picture on the right shows the deuterium-tritium reaction, which is two isotopes of hydrogen. And when they fuse together, it produces helium and a neutron. Now, there are trillions of natural fusions taking place right now at the center of stars like our sun. And in fact, nearly all of the natural light in our universe ultimately arises from fusion. A power station based on fusion has many, many benefits, or would have many benefits. It's an inherently safe source of low carbon nuclear energy. There's no risk or no chance of a runaway chain reaction, which is a problem that conventional fission-based nuclear power stations suffer with. It would also be very sustainable. Produces no carbon at all, and it could potentially meet global clean energy demands for millennia. So how do we make fusion happen? A special device was invented called the tokamak, which is essentially a magnetic bottle in which we confine a very hot plasma. Now, I say the word plasma, essentially it's all you need to know about plasma is when gases get extremely hot, they become electrically conductive. And when I say extremely hot, it's mind-boggling how hot these gases get in fusion. To get fusion to happen, you need to heat your gases up to about 150 to 300 million degrees, which is one of the hottest things in the universe. Now, a tokamak is a very special device because it uses very strong magnets to heat and confine this hot plasma of hydrogen nuclei. If you didn't have the magnets that are part of the tokamak, the gas and the plasma would lose all of its heat energy to the walls of the vessel, and you'd never get anywhere near hot enough for fusion to happen. So if we know how fusion works, and we have a device that can make fusion happen, then why don't we have fusion as a commercially viable source of electricity right now? And that's because there's a number of residual technical challenges that need to be solved before we can make it happen, which I'll talk about now. So challenge number one is tritium. So deuterium and tritium are the two primary fuels that you need to get fusion to work. And although deuterium is quite widely available and can be extracted from seawater, tritium is very, very difficult to produce, and it's very rarely found naturally on Earth. In fact, there's only about 20 kilograms of tritium produced globally each year. A single fusion power station may need about 200 kilograms per year, so you can see that there's simply not enough tritium being produced to sustain a fusion power program. And we're actually building a very large tokamak in the south of France. It's an international mega project. Governments from all around the world have come together to try to solve some of the technical challenges of fusion. But this project, ITER, will use up the world's stockpile of tritium. So in order for fusion to become a reality, we need to find a reliable supply of tritium. Now, this picture of a watch is quite interesting because it's the glow-in-the-dark parts of the dial are actually tritium paint. And we used to use tritium paint to make these kind of glow-in-the-dark things, which was a tremendous waste of a very valuable resource. Challenge number two is all about plasma exhaust. So with the deuterium-tritium reaction, it produces helium, and this helium is actually an impurity, and we have to remove this from the tokamak to keep the fusion reaction going and to keep the plasma burning. And this means that contact between the extremely hot plasma and the wall of the tokamak is unavoidable. So where the plasma comes into contact with the tokamak wall, these plasma-facing surfaces have to withstand incredible heat loads. And these are about 10 times greater than those experienced by a spacecraft during re-entry. And it's important to consider that whereas a spacecraft only needs to land once or a couple of times if you're SpaceX, a fusion power needs to operate continuously and reliably for about 20 years. So we need high temperature materials that are very resilient and able to cope with these heat fluxes over long durations. Challenge number 3 is all about the plasma itself. So fusion plasmas are magnetic, they're charged, and they're very, very hot. Tiny changes in density, electric field, or temperature can rapidly propagate and cause instabilities that challenge the magnetic confinement and cause the plasma to become unstable. Essentially what happens is the plasma can get so unstable that it crashes into the walls of the tokamak, which you can see in the pictures on the left and right of this slide. And the picture in the middle shows some of the damage that can occur when this happens. So these instabilities are a real problem because the kind of damage that you see here is not really acceptable in a long-term commercial power station. So before a fusion power program can be developed, we have to find better ways of confining the plasma and reducing the likelihood of these kind of events. So these are the 3 major problems. I'm going to talk now about some of the solutions. And the first one deals with tritium. So as I mentioned, tritium, one of the fuels used for fusion, is incredibly rare, and we need to find a reliable source of tritium for fusion to become a reality. And people have thought about this, and they've come up with these tritium breeder blankets. And one of the byproducts of the DT reaction is a high energy neutron. Now, lithium-7, which is an isotope of lithium, has a very special property that when it's hit by a neutron, it splits and produces tritium and some more helium. So by wrapping the tokamak walls in a blanket of lithium-7, it's hoped that we can use these neutrons to breed more tritium fuel, which we can then pump back into the reactor and keep the fusion reaction going. And this could hopefully make fusion power stations tritium self-sufficient. And actually the ITER project in the south of France is going to be trialing some tritium breeder blankets that will hope demonstrate this concept and pave the way for tritium self-sufficiency. I'm now going to pass over to Tristan, who's going to talk to you about high heat flux materials.
Yes, so the second solution addresses the problem of very high heat fluxes. As James explained, in the nuclear reactor, we've got a very, very high temperature plasma, which is radiating heat and creating those heat fluxes that can reach 20 megawatts per square meter. And this heat has got to be extracted and then used to produce electricity. The heat fluxes we're dealing with are enormous, and they can be up to 20 megawatts per square meter. If we put that into other figures, or in other words, it's about 500,000 light bulbs being lighting a square meter of space. And this heat flux is actually enough to melt a ton of steel in under a minute. So we need to come up with cooling designs and materials that are able to sustain those heat fluxes. And that's why we're using, for instance, refractory metals, which are mainly tungsten and beryllium, which is going to be used in the experimental fusion reactor in the south of France, ITER. And we combine those with high conductivity metals, such as copper, and also structural steel, to come up with cooling designs, such as the graph, the one shown in the top right graph, where you got piping copper, which is in ties of tungsten, and it allows to extract the heat as fast as possible and then to create the electricity. And on the bottom of the slide, you can see the current design, which will be used in the ITER experimental reactor. So now we can move to a solution to the third problem which we have, which was about the plasma and how to control the plasma and confine it so as to increase the fusion reactor, the number of fusion reactors. So what we're using is superconductive magnets. And those magnets are allowed to, as James explained, to confine the plasma and to increase the density and the probability of an fusion reaction occurring inside the tokamak. And as you can see from the 3 bullet points, there has been some increasing progress with magnets. First, JET, the first international reactor built in 1982, was only using copper, which is not superconductive. And the problem with copper is that when we pass current through the magnets, they're going to heat up a lot. So the confinement that we got from the magnets was actually limited, and only 3.45 Tesla was achieved for JET. For ITER, which is meant to produce its first plasma in 2025, superconductive magnet combining titanium to niobium will be able to generate higher, will be better magnets because they'll have better properties for confining the plasma, and they'll be reaching values of 11.8 Tesla, and also have a critical temperature below which they are superconductive. And when they're superconductive, they don't produce heat when current is being run through them. So this got, the use of superconductive magnets got very strong merits, notably allowing for stronger magnetic field. And it also means that less cooling is required to make the magnets work, and we get better plasma control, and this allows us to develop smaller and more efficient tokamaks in the future. On the top right, you can see examples of the superconductive magnets that are being developed, and on the bottom, you can see that the magnets are actually all around the tokamak and represent very high proportion of the material being used in the tokamak. So now that we've talked about the current challenges that we have in the solutions, we can try to place fusion energy in context with all the other energies. And we're going to start with the economics of nuclear fusion. So we can compare the economic cost of the electricity market price with the prediction of the electricity generated from nuclear fusion. And as you can see, the current market price for electricity is about 40 to 50 pounds per megawatt hours. However, most predictions say that the first electricity generation by fusion is going to be above 100 pounds per megawatt hour. So if we only look at the economics, actually nuclear fusion is not viable. But we need to remember that this is not the only parameter we need to consider, and there are many other parameters. For instance, we could think about the social cost of carbon in a context with climate change and the targets to achieve net zero in Europe by 2050. But there's also fuel security, storage requirements, and also the available resources that we have to build the power stations to use electricity for our societies. What about the recyclability of materials, the power density, the waste, and the pollution? We all need to address and consider those parameters in order to say whether fusion is viable. And those are just a few, and as you can see on the bottom, I've linked all the different parameters I could think about, and there are many, many that we could consider, but for the rest of this presentation, we're just going to focus on two, and those are going to be power density and also the available resources that we have at our disposal. So power density. This actually graph comes from a book which I recommend. It's a book written by David McKay, which was a professor at Cambridge, and the title of the book is Sustainable Energy Without the Hot Air. And it's actually a reference in the field of energy and energy systems. And in this book, David McKay explores the different ways we have at our disposal to produce electricity and compares them and see what energy plans, for instance, the UK could have in order to achieve net zero in the future and still produce great amount of electricity. One of the best graphs of this book is the one I've shown you here. On the y-axis, you can see the energy consumption per person. And on the x-axis, you've got the population density. And on this graph, most countries have been placed, and also the power density of different energy sources, you can see the green lines here, have been placed on the graph. And what you can deduct from this graph is the more the country is developed, the more likely it is to be located on the top right of the graph. Meaning that to sustain its energy needs, it needs to find very, very power dense sources to produce electricity. And actually, some energy sources have problems here, but nuclear fusion as a conventional power plant would probably achieve energy densities, power densities about 1,000 watts per square meter, which is enough to power the needs of any countries that on Earth today. The last point I want to discuss is the available resources we have to produce energy. Our societies consume more and more energy. If you look at the bottom right of the chart, you can see the world energy use across the years. And from 2000, where we consume about 14 terawatt years, we're now consuming years, and we'll probably be consuming 30 terawatt years based on the International Energy Agency report in 2019. And in the context of climate change and targets of phasing out fossil fuels, you can see that the resources that we have at our disposal to produce electricity are actually pretty slim in comparison to the world energy use. If we need to get rid of coal, petroleum, natural gas, we only have solar and the different renewable energy sources to produce the energy that we need. Uranium is going to run out at some point. We don't know when, but at some point. And I think in this context that fusion could help us produce the energy that we need. But this is only part of the question. We would also need to look at the metal resources that we've got available and also ask the question about the exponential increase of energy consumption of the world and know if it's sustainable and fusion could, if fusion can actually help to produce the electricity we need. So to conclude, I'd like to give a bit of context and also answer the question, where are we in terms of fusion power? So as you can see on the top right graph, until the year 2000, there has been very, very quick and exponential progress of nuclear fusion. So here on the graph, you've got the throughput product, which is the product of the temperature achieved for the plasma multiplied by the plasma density. So this is linked with the confinement produced by the magnets multiplied by the confinement time. And we have got a very, very nice increase from 1960 to the years 2000. But past 2000, you've seen that there has been a decrease of the pace of progress, but we're getting very, very close to achieving fusion. And I like to say that most people think fusion is 30 years away, but now we've got politicians that actually say, like Boris Johnson, that we're on the verge of nuclear fusion and that it could actually occur by 2040. As a reminder, ITER will achieve probably its first plasma in 2025, and we've got also a lot of hope with the development of more compact tokamaks, such as STEP and Mass Upgrade in UK, which might be maybe the first to achieve, to prove that nuclear fusion can be achieved within tokamaks. And the last bit is putting fusion in context of our world energy use. So on the next slide, we can see that we've got an exponential increase of energy use, and as we need to phase out fossil fuels, we need something to replace the energy we produce, and we believe that fusion here could play a big role into our energy future. Thank you for listening, and now we'll take a few questions from James.